Aho, welcome back again, everybody. Today we're doing section 1.5, and this section is all about how algebra and geometry are best friends forever and ever, BFFAE. I know it's kind of a funny title, but today we're going to talk about the connection between those two fields of math, and we're going to see it in action in a few ways. Let me pull up the slides, and we'll get started. All right. So yeah, section 1.5, here's the overview. There's a motivation for this. It's called algebraic geometry. We're going to talk about that a little bit just to give you some perspective of what's on the mathematical horizon and why we are seeing these deep connections. So that's the first part. Then we're going to talk about the real line again. We discussed it earlier back in section 1.2. We're going to talk about it again today. Then we're going to talk about the Cartesian plane, which is just like the XY plane that you know from the past. We're going to talk about the Pythagorean theorem and the distance formula, and we're going to see how they are essentially one and the same. Then we're going to shift gears just a tiny bit and talk about vectors, which essentially allow us to describe direction in space. Then we're going to talk about geometric vector arithmetic, doing arithmetic with vectors geometrically, then algebraic vector arithmetic, doing algebra with vectors. Then we're going to talk about standard basis vectors, which are essentially a way for us to decompose any vector into its constituent parts. You can kind of think of it like that. Then we're going to finish up by taking an eye toward higher dimensions, because with everything that we're studying in this class and everything that you talk about in calculus, you really want to think, how could I generalize this to higher dimensions? You want to have that like right on like the tip of your brain, like, what if this were higher dimensional? So we'll talk about that. So let's start with a bit of motivation. I like to ask this question in all of my classes. So I'll do this when we have the activity hour. So you might have found in the past that you were better at algebra or better at geometry. So show of hands, who is better at algebra? Okay, no one's in front of me, but who was better at geometry? Right. Okay. Well, good news, everybody. Algebra and geometry are BFFAE. They are best friends forever and ever. Basically, for every algebraic interpretation of a concept, there's a geometric interpretation of that concept as well, and vice versa. Oh yeah, I have this little note. So just a note here. The title of this section is a totally invalid use of mathematical notation. Do not abuse the equal sign this way. Okay. Um, Algebra and geometry may be BFFAE, but don't abuse the equal sign this way. I just couldn't help it because it was so funny. Um, anyway, back to what I was saying. So, what I'm saying is that what you witness when you're doing algebra has a geometric equivalent, and what you witness when you're doing geometry has an algebraic equivalent, and you can pass back and forth between the two, and you want to develop that skill. So, we're going to work on that in this class a lot. Right. Now, the reason there is this connection is actually very deep and nuanced, and it's so profound that it spawned what's called algebraic geometry, which is even now a very active field of pure math research. So, algebraic geometry, if you're interested, you can read about it there. It's a very deep rabbit hole to go down. Just a warning, many, many, many years deep. That's how deep I'm talking about. Um, Now there's this really important theorem called Hilbert's Nullstellensatz, and it's a graduate level mathematics theorem that asserts the beautiful connection between algebra and geometry. Uh, Basically, the Nullstellensatz is like a generalization of a theorem that we will learn, the fundamental theorem of algebra. We're going to talk about that in chapter 3. Or another way you could think about it is that the fundamental theorem of algebra is just a special case of this higher theorem called Hilbert's Nullstellensatz. Yeah, that's another way you could think of it. The Nullstellensatz is like the most general way of describing it. And then when you look at what we talk about in this class, you get what's called the fundamental theorem of algebra. All right, chapter 3. So, one thing I want to reassure everybody here is you don't need to worry about these highfalutin, complicated theorems that are from graduate school. Like, you don't need to worry about that. What we do need to worry about is what we study algebraically has a corresponding geometric interpretation. That's the big idea, and vice versa. So, I want you to practice that. Okay, so let's talk about the real line again. So what we saw back in section 1.2 is you can interpret the set of real numbers as a continuous unbroken line that we call the real line, right? So what this means is every number Every real number is located on that line, and every point on that line corresponds to a real number. All right. So, what I'm saying is, if you give me a real number, any real number, I can point to it on this line. Or if you pick any point on this line, it corresponds to a real number that I can tell you what it is. That's the idea. Okay. Um, yeah, so now algebraically, we can add and we can subtract and we can multiply real numbers. And this has a geometric interpretation that you can witness on the real line. So when you're adding two real numbers, you get a different real number. Possibly you might get the same number if you add zero, right? So geometrically, what this corresponds to is picking a point and then moving left or right depending on the sign of what you're adding, right? But the two interpretations are equivalent. So when you're doing this arithmetic, think about what's going on geometrically as well, like we're going to see right here. So let's look at 2 plus 3 for a second. 2 plus 3 algebraically or maybe arithmetically looks like this. I'm taking 2, I'm adding 3, combining, and I get 5, right? Geometrically, what's happening is this. It's like starting at the number 2 and going 3 units to the right to end up at the number 5. That's the geometric interpretation. Or how about this? Here I'm subtracting -3. So subtracting a negative is adding, right? So this is like starting at 2 and we're taking away -3, which means we're adding 3 and we end up at 5. Right? Now, if you were subtracting a positive number, so for example, 24 minus 6, that's like starting at 24 here and then going to the left 6 units. 24 minus 6, you end up at the number 18. That's the geometric interpretation, all right? Okay, now let's talk a little bit about the Cartesian plane. Um, I'm assuming most of you have seen the XY plane in the past. That's really all this is. It was originally developed by Rene Descartes. That's why it's called the Cartesian plane. It's basically taking two real lines and crossing them in a perpendicular way. So the way that the Cartesian coordinate system works is it uses an ordered pair, right here, x comma y, to determine the location of a point in the plane. And this is very similar to what I was talking about with the real line, in that if you pick any point on the plane, there's an ordered pair that corresponds to that point. And if you give me any ordered pair of two numbers, x and y, it corresponds to a point on the plane. So there's that correspondence there. That's what's going on. Um, Now, what are these two numbers? So the values x and y, they correspond to the horizontal and vertical displacement from, or I should say, along the x and y axes. That's the basic idea, right? So here I've got the point A comma B. I can zoom in and, oh, nope, can't zoom in. Sorry. This is the point A comma B. So it's A units this way and B units this way, and you end up right there. That's it. Now the two axes, they meet at the point 0 comma 0. That's what we call the origin. And like I mentioned, the location of any point can be described in this way. That's what's so nice about it. Okay, now that we're kind of refreshed about the Cartesian plane and the Cartesian coordinate system, let's talk about a critically important theorem called the Pythagorean theorem. This is like one of the most famous theorems in mathematics. I'm assuming you all have heard of it before, but it says this. If you're given any right triangle with legs of length A and B and a hypotenuse of length C, that's this thing right here, then the following equality holds. A squared plus B squared equals C squared. That's the idea. Now, this is the algebraic interpretation of that theorem. Let's look at the geometry for a minute. So A is the length of this line segment, and B is the length of this line segment, and C is the length of this line segment. And what this theorem does is it gives you a relationship between the squares of these lengths. So quite literally, it means if you take this number and you square it, you take this number and you square it, you add the two together, then what you're going to get is you're going to get this number, this length, squared. Now, remember what I said back in section 1.1. Multiplication can always be interpreted as an area. So this is a very direct, clear, geometric thing, and it always works. So it's gonna kind of go off the page here, but what is a squared? it's A times A, right? So quite literally, it's this length A times this length A again. And sorry, I can't draw the full square. And the area of that square is A squared. Now, what's B squared? B squared is B times B. So if we have another square coming off here, all right, this is length B. Oh, that's length A too, right? So the area of this is B squared. This is A squared. So what the Pythagorean theorem is saying is that if you take A squared and you add it to B squared, you're going to get the length of C squared. So here's C times C. A little bit messy, but this is C squared. There you go. So if you take this area and you add it to this area, you're going to get this area. And that's the geometric interpretation. Algebra and geometry, BFFs. Okay, now with that being said, let me clear this out. Oops. Let me clear this out of the way for a sec. Let's look at another very intimately related theorem called the distance formula. So I'm sure some of you have heard of this before. I doubt all of you remember it. Hopefully, after this, you will never forget it because the connection between the distance formula and Pythagorean theorem is, I mean, they are the same. They are basically the same. So let's read it together here. So the distance formula says the distance between any 2 points A and B in the plane is given by this formula. So A we're going to describe as an ordered pair, x1, y1. B we're going to describe as a different ordered pair, x2, y2. They could even be the same, but if they're the same point, then the distance is zero. Not very interesting. Or at least not in this context. So this symbol over here just means the distance between A and B. That's what that notation is meaning. And this is the actual formula for computing the distance between those 2 points. All right? Okay. Now we are going to prove this. The proof is actually quite short and it's very, I don't know, it's very edifying. So we're going to go through it right now. Here's the proof. Let x1 and y1, I'm sorry, x1, y1 and x2, y2 be given points on the plane. They could be any 2 points you want. Now, the line connecting those 2 points, here they are on the picture, the line connecting those 2 points, that forms the hypotenuse of a right triangle, right? Because you could just go this way, and now you've got a right triangle, just like that, okay? Now, because this is a right triangle, we can use the Pythagorean theorem to find the length of this hypotenuse. And the length of that hypotenuse is equal to the distance between those 2 points. That's the idea. So the Pythagorean theorem and the distance formula are one and the same. It's just that the Pythagorean theorem is giving you results in planar geometry, and the distance formula is giving you results in what we call coordinate geometry, where coordinates are involved. Let's go through the calculation here. You're going to love this. So d squared equals a squared plus b squared, Pythagorean theorem. Now we just need to find expressions for a and b. Now remember, a is the length of this line segment. So it's the distance between these 2 points. Now, how do you find the distance between 2 points? Hmm. Does that sound familiar? How do you describe the distance between 2 points? Think about it. We talked about it before. Okay, say something out loud. What is it? What is the distance between the 2 points? That's right. It's the absolute value of their difference, right? So if we want to find this length, we just need to take the difference between the x coordinates and then take the absolute value. And that's exactly what's going on right here. So maybe I'll highlight this, use blue. So what is A? A is the absolute value of x2 minus x1. Okay, now do the same thing for the y coordinates, right? Do the same thing. What's the distance, or sorry, what's the length of this segment? It's the distance between the y coordinates of those 2 points. So we're going to get this. Let me highlight this in green. B is the absolute value of y2 minus y1. And the squaring is still occurring. The square is still the square. All right. Now we're pretty much done. Now what we need to do is we need to take the square root of both sides of this equation. One thing I'm going to tell you now, and I will repeat it throughout the course, and you should carry it with you through all of your math classes. Anytime you take a square root, you must include a plus minus. Every time. There is no situation where you do not include a plus minus. What happens is you include the plus minus, and then depending on the context of your problem, you may be able to toss out one of the two cases. That's what happens. So play it safe. Remember, you always include a plus minus. Always, always, always. I'm going to do it right now. Here we go. I'm going to take the square root of both sides, but when I do, I get a plus minus. Okay, now what is the problem we're trying to solve? We're trying to find the distance between 2 points. And at least in this reality, distance cannot be negative. So we're going to eliminate the negative case. We're going to eliminate the negative case. Now we've just got the positive square root. And then voila, there it is. That's the distance formula. So hopefully you never forget it. Um, Tiny little note here, there's one slight difference from this step to this step, but the difference really doesn't matter. Here I was able to get rid of the absolute value bars. That's only because squaring a number always gives you a positive number. It doesn't matter if you square a negative number or a positive number, the result is always going to be positive. So even if this result was negative, squaring it is going to make it positive. So in this case, the absolute value doesn't really matter. However, I feel like this is more explanatory, right? That's really what's happening. Distance between the x coordinates, distance between the y coordinates. That is how we're computing the distance formula. That's what's going on. All right, now let's use it, okay? And I want you to try this on your own. See if you can find the distance between these 2 points, 4, -6, -1, 9. All right, so think about it on your own for a sec. Okay, now say something out loud about what you're going to do. Remember, you don't need to say it to anybody. You could say it to yourself, or you could say it to your dog, your cat, your water cup, whatever. Okay, and now try to work it out on your own, and then we'll do it together. Okay. All right. So here we go. We've got our 2 points. We know our distance formula, the Pythagorean theorem. We just need to kind of plug and play. So here we go. There's our formula. Oh, one note I'll give. It actually doesn't matter which point you choose. You could choose whichever, sorry. It doesn't matter which point you call number one and which one you call number two. You can choose whichever one you want to call the first one. Doesn't matter. The result will be the same. So we'll call this one the first point, x1, oops, y1, and we'll call this the second point. Hey, x2, y2, like so. Now we can plug everything in, right? So you plug it all in, we get this. Simplify in the parentheses, you get this. Hey, okay, square 5 squared is 25. 15 squared is 225. So you add those up and you get 250. Now, a little note that I'll make here. At this point, it's pretty much solved. The distance between those 2 points is the square root of 250. But you could simplify that radical a little bit more because this number contains a perfect square factor. In particular, it has the number 25 baked into it as a factor. So you could simplify it more, which is what I'm showing right here, but this answer is still valid. That's a correct answer. It's just not fully simplified. So we're going to fully simplify it here. And what we're going to do is we're going to factor 250 into 25 times 10, just like so. And then using properties of radicals, we can actually split it into a product of two radicals. We'll talk about that in chapter 4. And then the square root of 25 is 5, and square root of 10 is some irrational number. There's no way to simplify it. This is the cleanest the square root of 10 will ever look. There you go. All right. So now we're going to shift gears a tiny bit and we're going to talk about vectors. Talk about vectors here. So the basic idea is this. Just like we saw with the Cartesian coordinate system, we were able to use points to describe locations in space. Now what we need is we need a way to describe direction in space, like which way to go. Points give you locations. Dit, 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 dit. That's what you get there. Now I want to talk about going this way in space and going that way in space. That's the goal at this point. So we do that with what are called vectors. So what is a vector? A vector is a geometric object that has both magnitude and direction. So here is a visual representation of a vector. A lot of times we represent them as arrows, all right? So intuitively, a vector just says which direction to travel and how far to go. That's the basic way of thinking of a vector. So when you think about a vector, think about it like that. It's telling you which way to go and how far. Most of the time, maybe not most of the time, a lot of times, vectors are represented by arrows like so, to say which direction you're traveling. And a lot of times we will use the length of that arrow to represent the magnitude of the vector, which we'll talk about in a minute. It's basically the length, it's how far to travel, and the direction is the direction. Now, symbolically, how do we write these things down? We typically use bold letters to represent a vector, or we will put a little arrow over the letter itself, right? I can zoom in on that a little bit. There we go, just like that. That's because, if you've ever tried to draw a bold letter by hand, it can be kind of difficult, right? Like, how do you make it bold? I guess you could color over it a bunch of times. Well, if you're too lazy to do that, you can just go like that. Oh yeah, sometimes the arrow will have one, sometimes it'll be two. I know in physics, a lot of times they will use a hat, for example. That's up to your physics instructor. There's lots of ways to write vectors, but we do need to distinguish them from scalars in some way, at least at this stage. Scalars we're going to talk about in a second here. All right, but let's talk about a displacement vector first. So imagine that a particle moves from point A to point B. Then the corresponding displacement vector, v, it has an initial point, a terminal point, b, and what we can do is we can write that vector v that goes from A to B, or I should say from A to B. Yeah, goes from A to B. We can write it like so. We can write AB with a little arrow over the top indicating that we're going from A to B. That's the idea, okay? And we call that the displacement vector. Now, two vectors are called equivalent or equal if they have the same direction and they have the same size. So what I've got pictured right here, those are two equivalent vectors. It doesn't matter that they're passing between different points. This one's going from A to B, this one's going from C to D. That doesn't matter. What matters is that the direction traveled is the same and the distance traveled is the same. And if that's the case, then those two vectors are said to be the same vector. They're equal, they're equivalent, okay? All right. Now, the zero vector is a special vector, but we denote it by a bold zero or a zero with an arrow on the top. And it's the only vector that doesn't have a direction. It could be any direction, it could have no direction. It's the only vector like that, but there is a zero vector. Okay. Now, let's do a little bit of arithmetic, geometric arithmetic with these vectors. So I used this word earlier, just like a minute ago. A scalar is just a real or complex number. In this class, in this context, you can just assume that a scalar is a real number. And what we're going to do with these scalars is we're going to compute scalar multiples of a vector. And quite literally, what this does is it takes your vector and stretches it or squishes it or flips it in the opposite direction. Wait, flips it in the opposite direction. Sorry, it's kind of hard to do. Um, so that's what a scalar multiple of a vector is, and that's why that word scalar is so nice. So let's go through the details. If k is a scalar, a real number, and v is a vector, direction with magnitude, then the scalar multiple of v is denoted by k times v, and it's the vector whose length is absolute value of k times the length of v. So the absolute value of k is the amount of the stretch or compression. Right? Now, if k is positive, then the direction of kv is the same as v. If k is negative, then the direction of kv is the opposite of v. You've flipped the vector 180 degrees, spun it around in the other direction. If k is 0 or if v is the 0 vector, then kv is just the 0 vector. All right. So here I've got some pictures, some examples of it right down here. Here's the vector v. Now, if I take that vector v and I scale it by a factor of 1/2, then I get half v. And quite literally, it is, there you go, it is taking the vector v and squishing it by a factor of 1/2. It's going like that. You can see, like, if this is the length of v, this is half the length of v, right? But again, that scalar could be any size. So here what I did was I took v and I scaled it by 1/2. So if I scale it by 1/2, I've got 1v plus a half of a v, which is 1/2 v's. So if this is v, this is 1/2 v's. So you see how these things are really just stretching and squishing. That's really what the scaling is doing. Now, if you multiply by a negative number, what that does is it basically rotates the vector 180 degrees and it's pointing in the exact opposite direction. So if it was pointing this direction and you multiply it by -1, now it's going to point in that direction. Because I multiplied by -1 and the length or the size of -1 is 1, I haven't stretched the arrow out at all. All I've done is flipped it around. So here's v, here's -v. Not too bad, right? That's how this works with scalar multiplications. And this is how we can define negative vectors. So what is the vector -v? It is quite literally -1 times v. It's got the same length as v, it just points in the opposite direction. Here you go. Here's v, here's -v. And now that we have this notion of scalar multiples of vectors, we can talk about parallel vectors. So two non-zero vectors are parallel if they're scalar multiples of one another, right? So you've heard the word parallel before, I'm sure. It means the exact same thing as it meant before. It just means the two things are parallel. They don't intersect, right? If they were to continue on forever, they would never intersect. So actually on this slide, every vector you see in this picture is parallel, right? And it even makes sense intuitively, right? These lines that I'm sketching, they're all parallel to each other. They're not going to like tip and touch each other at some point in time, right? They're parallel. So how do you define a parallel vector? Just a scalar multiple of the other vector. That's it. Okay. All right, now let's talk about vector addition. So we've got these vectors, we know how to stretch them, we know how to flip them around. Maybe, how do you add them together? Let's talk about that. So let's say we have two different vectors, u and v. U goes from A to B, and v goes from B to C. Then the sum of those two vectors, u plus v, is the vector that goes from A to C. So intuitively, when you're adding two vectors, what you're doing is you're connecting the vectors from tip to tail, and then you're going to draw the line or the vector that connects the initial point at the very beginning to the terminal point at the very end, just like what's pictured here. So here's the vector u, here's the vector v, and the vector u plus v is this one, just like that, just like that. And that's it. So there you go. One little side note I'm going to make right now. I had talked about the triangle inequality in the last section, and I had mentioned that it's a little bit easier to understand in terms of vectors. So I'm going to do a little sidestep right now and talk about it here. Um, think about this. Each one of these vectors has a length. So now I'll say the length is like this, absolute value bars of u. That's the length of this arrow that you see here. And then v also has a length, right? And then this vector also has a length. And so what the triangle inequality is saying, or if you don't remember it, it says this. It says the length of u plus v is always less than or equal to the length of u plus the length of v. And it's really easy to see geometrically now, right? Because what it's saying is that if you travel this distance in this direction and then you travel this distance in that direction, that's always going to be more or equal to going straight from A to C. I always like to think about it as if you go from home to the store and then from the store to school, the distance traveled will always be greater than or equal to if you had just gone straight from home to school. The only time it will be equal is if the store is on the path of that vector. That's the only time it'll be equal, right? There you go. So that's the triangle inequality for vectors. Okay, now let's do some practice. Let's sketch the sum of these two vectors, A and B. And I do want you to try this on your own. If you've got the fill-in notes, you can kind of just trace the length. You might want to use a ruler. If you've got a tablet, it's even easier. I'm going to do it right here in just a minute. But I want you to think about what you're going to do first. Okay? Now, say anything out loud about how you're going to do it. You can say it to your dog, your cat, to your hand, to your computer. Just say something out loud to give your brain that feedback. Okay? And now try to work it out on your own. Remember, if you need to pause the video, that's fine. I mean, you should because I don't give a lot of time to do it. You can pause it. That's totally fine. And we'll do it together in a moment. Right. Okay, here we go. So I'm going to add those two vectors. So let me just trace them a little bit. Maybe I'll say, okay, here's the vector A. I'm just tracing them on my tablet here. Here's the vector B. B, oh, I should label these. A, oops. Okay, now what I'm going to do is this. So if I'm doing A plus B, right, that's what this is going to be. This is going to be A plus B. So if I'm adding those two things together, I'm going to travel along A, and then I'm going to travel along B. So I'm going to put them, again, tip to tail, like so. And then the vector sum is just going from the tail of A to the tip of B. So maybe I'll use, I don't know, pink or something. So I'm going to start here, and I'm going to go there, and then this is A plus B, like so. That's the vector sum. There you go. And that's what it looks like geometrically. So we can add these two things geometrically. Let's do a more complicated example. Using the same vectors, what I want you to try now, and I do want you to try this one on your own, I want you to try to sketch this vector, A minus 2B, right? So once again, think about this one for a sec. Okay. Say something out loud about what you're going to do. Maybe what do you notice that's different about this example than the previous one? And now try to work it out on your own, and we will do it together in just a moment. Okay. Here we go. All right. So first thing I notice is this. I don't know about you, but I see negative 2b. So that means we're going to need to flip b around because negative b goes in the opposite direction of b, and we're going to need two of them. So let me start with that. I think I used red in the past. So, okay, if this, well, I'll say this, if this is b, then negative b should go the other way, like that. Okay, so there's negative b. And I'm going to need two of them. So I'm going to cheat a little bit and use my tablet to just duplicate this. Um, okay, so there's two B's right there. There's two B's. Now I need A. So let me copy A here. A looks like this. All right. And we're doing A plus negative 2B. In fact, let me even write that. I'm going to see this as A plus negative 2B. Okay. All right. So here's A. Right, there's A. And again, we're doing tip to tail. So here's A, and then I'm going to take this, oops, I'm going to take negative 2B and I'm going to put it right here. Let me move this a bit, give myself some space. So what is A minus 2B? Oops. A minus 2B is going to look like this. I'm going to go from here to there. So this is A minus 2B, just like so. That's A minus 2B, or A plus negative 2B. And that's it. So that's geometric vector arithmetic. Stretching, squishing, adding, subtracting, multiplying by -1. We can do all of that, and there's the geometric interpretation. Now, let's take a look at the algebraic interpretation of those. So we saw how to do all of this geometrically. Let's switch and look at the algebra instead. So first we need to talk about what's called a position vector. So if we have a vector v and we place the initial point at the origin, then the terminal point lies here, and we could give that point the coordinates v1, v2, where v1 and v2 are called the components of the vector. So the components of the vector are just describing how far and in which direction to travel in the horizontal and vertical directions, right? So maybe I could even denote it like so. This here is v1, and this here is v2 in this case, because I'm talking about the position vector. So I'm starting at the origin and going to v1, v2. All right. So these things here, v1 and v2, are called the components of the vector. And we can express this vector algebraically like this. V equals v1, v2. One thing I want to point out here, though, is that these are angled brackets. They are not parentheses. They are not parentheses. They're angled brackets. See? It's like and we use those to indicate a vector. So again, we're distinguishing between points and vectors. Points and vectors are not the same thing. I think I say that in the next slide. Let me check. Yeah. Vectors are not points. They are different. Vectors are like arrows, right? They're arrows with a direction and a magnitude, directions and distances. This is why we're using those angle brackets instead of a parentheses, right? So remember that any two vectors that have the same direction and length are equivalent. So there are infinitely many equivalent vectors. And actually, what I've got pictured over here, can't see, I can't zoom. Oh, I can zoom in on part of it. Here, all the vectors that you see in this diagram, they're equivalent. Those are equivalent vectors. They're the same vector. The only thing that's differentiating them is where you're placing them. This right here, this is actually the position vector, the one that's right at the origin. That's the position vector. All right. But those are all equivalent vectors. All right. Now that we have an algebraic way of talking about vectors, we have an algebraic way of talking about the length of a vector. And here it is. This is going to look familiar. So the magnitude or the length of a vector is the length of any of its representations. And we denote it using the absolute value bars. Once again, it's like the distance, right? The distance from the tip to the tail, or the tail to the tip, I should say. Doesn't matter, it's distance. Sometimes books will use this like double bar, this double absolute value bar. That's okay. It's just the same thing. So how do we compute the actual length of these vectors? We use the distance formula. Aha! Yeah, we use the distance formula, kind of by the same argument as before. Whenever you've got a vector, I'll zoom in on this one, you could draw a horizontal component and a vertical component, and you get a right triangle. You can see, we're going to see this in a minute. You can decompose this thing into its horizontal and vertical components. Then we can square those things and add them together. There we go. So what is the length or the magnitude of a vector? You take the components, you square them, you add that up, and then you take the square root. Boom. And that's what we call the length of that vector. Right. Okay. Now we can talk about the displacement vector algebraically. So here we go. Before we had just talked about a displacement vector as going from A to B, right? Or from A to B. Wait, from A to B. There we go. From A to B. Now we can write it algebraically, and it looks like this. So the vector that goes from this point x1, y1 to this point x2, y2 is given by this vector. You take the difference in the x coordinates and you take the difference in the y coordinates, and that's your displacement vector. And this makes sense, right? Because x2 minus x1 is the displacement in the horizontal direction, and y2, y1 is the displacement in the vertical direction. That's it. So that's how you're getting the displacement vector from A to B. Okay. Now we can kind of put all of these things together. We talked about vector addition, we talked about vector subtraction, we talked about scalar multiplication. all of these have an algebraic equivalent. And so this is what it looks like. If we've got two vectors here, A is A1, A2, and B is B1, B2, and we've got some scalar K, well, if we add A and B, we're going to add them component-wise. So this plus this means add the two horizontal components and then add the two vertical components. And that's the vector sum. If you're doing subtraction, same thing. A1 minus B1, A2 minus B2. Now, if you want to scale the vector, you're going to do it component-wise also. So, pardon me. We're going to scale it just like we did before, but it's going to happen component-wise. So K times A, you're going to scale A1 and you're going to scale A2 to get KA1, KA2. So again, it's happening component-wise. And now what's cool is this actually corresponds with our geometric interpretation, right? So I've got these detailed pictures here and here. The scalar multiplication one is the easiest one, I think, right? So here's the vector A, and here are its components, A1 and A2, like so. If we wanted to stretch this thing by a factor of K, then what we're going to do is we're going to stretch each one of those components by a factor of K. Multiply A1 by K, multiply A2 by K, and then that's what you get. That's what you get right there. Same with vector, with a vector sum. Here's yeah, so like here's A, here's B, here's A plus B, right? Well, what is A1 plus B1? It's A1 plus B1. So it's like going this way. And then what's A2 plus B2? It's A2 plus B2. So it's going this way. And that gives you the vector A plus B. Algebra and geometry are BFFAE. There it is. They're just so intimately connected. Okay, now you're going to try it. You're going to try it, okay? So you don't have to do all of these if you don't want. You're going to get practice on the homework. You're going to get practice when we do the activity. But I want you to try this one on your own, okay? So let A be this vector, 4, 3, and let B be this vector, -2, 1. And I want you to find all of these things. The length of A plus B, A minus B, 3B, 2A plus 5B, okay? So think about it for just a minute. All right. Now say something out loud about what you're going to do. And then calculate it on your own, and we'll do it together. You can just pick a couple if you don't want to do all of them. That's fine. Okay, here we go. So we're going to do all of these, or I'll show you how to do all of them. Some of them might not be too bad. If you're comfortable with this, that's great. If not, we're going to work on it together in activity. But let's do the length first. So the length of A, we're just using the distance formula. Square the components of A, add the result, and then take the square root. 25, take the square root of 25, you get 5. What's A plus B? You add component-wise. 4 minus 2, 3 plus 1 gives you 2, 4. Subtraction. What's A minus B? You subtract component-wise. 4 minus -2, 3 minus 1 gives you 6, 2. What is 3b? Scalar multiplication. It occurs component-wise. So I'm going to do 3 times 2 and 3 times 1, and you get -6, 3. That's it. Now, the last part here is just putting all of it together. You can do all of this stuff, right? So I'm going to scale A by 2, scale B by 5, and then add the results. So this will give me 8, 6, -10, 5. Now I'm going to add those results component-wise. 8 minus 10, 6 plus 5, -2, 11. Boom, that's the vector. Cool stuff. Okay, now one of the reasons vectors are nice is because it lets us do things like this. And we're going to see this again later when we start talking about transformations of graphs. We'll see that in chapter 2, if I remember right. So think about this question for a minute. Let A be the point 6, -9, and let V be the vector 13, comma 4. So my question to you all is, where does the point A travel when it's moved along the vector V? So basically, start at this point, move along this vector, where do you end up? And then also, what if point A travels the same distance in the opposite direction of V, right? So what if you, like, think about that one too. So I want you to try this on your own. Think about it for a minute. Okay. Give yourself that audio feedback. Say something out loud to help your brain process these ideas. And then try to work out both parts on your own. Where is the point going to end up? Right. Okay, now let's do this together. Um, this isn't too bad if you think about it geometrically, right? So let me do a quick little sketch. I'm just going to do this. I'm going to say, here's the point A, right? Here's A. And what we're going to do is we're going to start at this point and we're going to move in this direction. So that means we're going to move in the positive x direction 13 units and the positive y direction 4 units. So essentially we're going to do this. We're going to go this way, and this is going to be 13, and this is going to be that, right? And that's going along this vector here. Here's the vector v. Okay, and when we do that, the point that we end up with is just going to be the coordinates of A shifted by that vector V. So 6 plus 13 is 19. -9 plus 4 is -5. And that's the result. So geometrically, that's what it looks like right there. I've got the algebraic result right here. And that's exactly what I was just saying, right? So you take this point and you shift the coordinates by this vector. And then you get this new point, 19, -5. Now, the second part of the question said, what if you go in the opposite direction of V? So let me go back to my picture for a second, move things away a little bit. So if this is V, negative V is taking the opposite of all the components, right? -13, -4. But the argument is still the same. We're going to do the same thing. Let me erase some of this stuff. Do, 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 do. Oops, no. That's okay. I can rewrite that part. Here we go. Give myself some more space. Okay, so there's the point A. Now we're going to move along negative V. So we need to go -13 in this direction, and then -4 in this direction. And this is the vector negative V. Okay, so where are we going to go? 6 minus 13 is, oh my gosh, can't do it in my head. -7. Is that right? Minus 13. I think so. I think so. I might be wrong. I can't do math. Um, -9 minus 4 is -13. There we go. There it is. -7, -13. And that's how we do that. And that's always how it's going to be. So you can move these points by using vectors to say where they're going to shift to. Okay. Now, continuing with vectors, the next thing we got to talk about are unit vectors. And these are a very important kind of vector. They're simple to understand. A unit vector is just a vector that has magnitude 1. It's a vector that has length 1. That's it. So more specifically, U is a unit vector if and only if its magnitude is 1. And these vectors are really important. We use them a lot, mainly because they kind of just give you a direction. And the length is 1, but a lot of times we want things to be length 1 because then we can stretch them and squish them however we want. All right. Um, so a lot of times what happens is this. A lot of times we're given a non-zero vector v, and we want to find a vector that's in the same direction, but has length 1, right? Is length 1. So we can do that through a process that's called normalization. We're going to normalize the vector. And all we really need to do is find the length of the vector and divide the vector by that length. So it sounds weirder than it actually is. It's actually pretty straightforward. So let's say we've got a vector v. What we're going to do is we're going to compute its length, its magnitude, and then we're going to do v divided by its length. So a unit vector in the direction of v is v divided by its length. Another way of writing it is this right here. Yeah, just v times 1 over its length. And down here, this is just the proof that indeed this is actually a unit vector, because the length of this vector here is the length of this vector using just properties of the distance formula or properties of square roots or whatever you want to say. You get this. Remember, the length of a length is the length again. And then any non-zero number divided by itself is equal to 1. So this is how you find a unit vector in the direction of any vector. That's how you do it. Okay, and now you're going to practice this. So same thing as before, I'm going to give you a vector v, and I want you to find a unit vector u that's in the same direction as v. All right, so think about it for a sec. Okay, now say something out loud about how you would do it. How would you find a unit vector for v? Right, and now try to work it out on your own. Here's a little hint. You're going to have to find the length of v, so start with that. Right. Okay, so first thing we got to do is find the length of v. So here we go. The length of v is the length of the vector negative 4, 3. We're going to use the distance formula again. Negative 4 squared plus 3 squared is 25. Square root of 25 is 5. So that is the length of v. Now we're just going to divide all the components by 5. That's all we got to do. That's it. So a unit vector in the direction of v is 1/5 times v. And now we can just distribute that scalar into the components like so. There you go. Do I verify it? I do verify it here. So here's one of those times where you can actually check your work. If you're not sure if you did it right, you can compute the length of this new vector, and you should get 1. You really should get 1. If you don't get 1, either something went wrong in your check or something went wrong in your calculation of the length. So here we go. We'll check it. So what's the length of u? Take the length of this vector. Same process. We're going to square the components and add them together. We get 16 over 25 plus 9 over 25. Merge the two fractions like so. 25 over 25 is 1. Square root of 1 is 1, and we're good. So that is actually a unit vector. Okay. Now that we know what unit vectors are, we can talk about something called the standard basis vectors. So another thing that we're going to do a lot in math and science is we want to take a vector and we want to decompose it into its horizontal and vertical components. You're going to do this a lot in physics. So physics majors pay close attention here. Pay close attention. You're going to get a vector and your instructor is going to say, okay, what is the horizontal component? What's the vertical component? Write this in terms of the standard basis vectors and so on, right? Now, just a little taste for the future, this idea can naturally extend to higher dimensions, but in this class, we'll just stick to 2 dimensions. Um, so how do we do it? If we want to decompose a vector into its horizontal and vertical components, we want to define 2 standard basis vectors. And here we go. Here's how we do it. These are the standard basis vectors for 2-dimensional space. Here they are. We denote one of them by a bold I, and it's the vector 1, 0. And the other one is a bold J, and it's the vector 0, 1. Here's a picture of what they look like. So here's the vector I, and here's the vector J. And really what these vectors are is they're just unit vectors in the x direction, the positive x direction, and the positive y direction. That's all it is. Yeah, so I is a unit vector in the positive horizontal direction. J is a unit vector in the positive vertical direction. Um, and that's really what we want. So we just want unit vectors in those perpendicular directions. Now here's the big idea. This is the takeaway from this, okay? What I'm saying is every single vector in 2 dimensions can be written in terms of I and j. It can be written in terms of those two standard basis vectors. That's why we call them basis vectors, because they kind of form the base of every other vector that you see on the plane. All right, so that's the big idea, that's the big takeaway, and I'm going to show you how right now. So think about this for a second. Let's say we have the vector 3, -2. What I can do is I can pull that vector apart and I can write it as the sum of these two vectors, right? So 3, 0 plus 0, 2. All I did was break it apart into its components, right? X, yeah, x component 0y, 0x, y component. Now I'm going to factor the constant out of this. So I'm going to factor a 3 out of both of these components here. And I get 3 times 1 comma 0. I'm going to factor -2 out of this one. I'm going to get -2 times 0 comma 1. But look, that's the standard basis vector in the x direction, the horizontal direction. This is the standard basis vector in the vertical direction. So this is I and this is j. So we can rewrite this vector in terms of i's and j's, and that's it. It sounds more complicated than it really is, but all we're really doing is saying, hey, this is 3i and this is -2j, and you add those two vectors together to get this one, just like so. Here I've actually got a picture of it drawn right here. So the vector that we were interested in is this purple one. This is the vector 3, -2. Add those two vectors, right? Add this vector and this vector, you're going to get this vector. You're basically just going, there it is, just like that. So how do we decompose it? We first decompose it into its component pieces, the horizontal component and the vertical component. That's right here. Then we're going to express the horizontal component and the vertical component in terms of the basis vectors. I've got those sketched right here. Those are the two standard basis vectors. So what is this vector? It's 3 times the horizontal basis vector. 1, 2, 3. Okay, what is this one? It's 2 times this vector, but in the opposite direction. So -1, -2. There it is. So now we've decomposed it. That's what you get. So you can do this with any vector. Any vector in the plane you can do this with. You're going to do it a lot in physics, okay? More generally, so we're just going to do full generality here. If you've got any vector A, here's how you can decompose it. You can say it's, well, this is the same process I did before, right? Split it into its component vectors, factor out the scalar, and then you'll be left with I and j. So this is the purely general way of writing this vector in terms of I and j. All right? Okay, so to close off here, the last thing I want you to do, this is already a lot, right? Is this. This is where you get to kind of dream and wonder, think about it while you're falling asleep, you know, dream about this stuff. So even though all the stuff we've been talking about is just going on in 2 dimensions, everything we've been talking about can be generalized to any number of dimensions that you want. Okay, so you should always wonder if and how a mathematical result will generalize to higher dimensions. I have to do this all the time in my math research. It was like I got a result for 2 dimensions, and then the next question was, how would I generalize this to any number of dimensions, right? So just like R2 is R cross R, it's 2-dimensional space. R3 is 3-dimensional space. You can describe points in 3-dimensional space using three coordinates, X, Y, and Z. So any of you that take Calc 3, any of you that take Calc 3 are going to see this. And don't shy away from thinking higher dimensionally. All of the interesting problems are higher dimensional. I'll talk about one in a sec. So more generally, take a deep breath. More generally, for any positive integer n, Rn is just R cross R cross R cross R n many times. Okay? And that's just n-dimensional Euclidean space. Yeah. You can use n-dimensional vectors as well. Just extend all the stuff we talked about vectors to any number of dimensions. Um, Now, here's where things get really interesting. It's really, really hard to visualize anything beyond three-dimensional space. That's just one of the limitations of being a human being. Sorry. Um, you can kind of visualize four-dimensional space, but once you get beyond that, our intuition for what it looks like visually is just gone, right? And that's why you need rigorous mathematics. There's a relationship between intuition and rigor, like we talked about in the very, very first lecture. This is why we need that rigor, because everything we're talking about can be generalized, but once we get into those higher dimensional spaces, our intuition disappears. A lot of it disappears, at least. Okay. The other thing is this. In practice, most of the interesting problems that we are currently interested in involve a high number of dimensions, a very high number of dimensions. Classic example is machine learning and AI, or maybe I should say a modern example is machine learning and AI. Um, One of the reasons that machine learning is such a popular thing today, it's a popular subject of research, is because it's an approximation method that overcomes what's called the curse of dimensionality. Generally speaking, the higher number of dimensions you have, the more complicated the problem becomes, right? And it can get to the point where it's intractable, meaning computers can't handle it anymore. But machine learning has a way of kind of getting around that using some clever mathematics that you all can read about later on. I think a very simple, easy to understand example of AI use is in optical character recognition, right? So um, you might have seen this before. If you have like a tablet and you write a math equation down, and then it recognizes the equation that you wrote down and then solves it, that's optical character recognition. It's looking at the physical like number that you wrote down and the physical symbols, and it's converting them into a text character, right? That's called optical character recognition. But even for something like that, it often involves 784 or more dimensions. Yeah, 784 dimensions to do something like that. And that's why we love computers. That's why you got to embrace technology, because that's not something that a human can handle, but a computer can handle it very well, right? So just to kind of finish things off, I just want to say higher dimensions can feel overwhelming, but just keep in mind you are a higher dimensional being too. Just take a deep breath and dive in. You will be okay. And you can always start small. Start with one dimension, two dimensions, three dimensions, and then ask yourself, how do I think it would extend to higher dimensions? Okay. On that note, let's play. So I'm excited to do all this stuff with you. I know this lecture was a little bit longer, but there's a lot of content to cover. Algebra and geometry, they're just so connected. We got to spend some time talking about it, right? I won't ramble on too much longer. Thank you all again for watching the lecture, and I will see you next time.